Hello and welcome to the Big Bang. Whenever the system is at unsteady state, then you can make the semi-infinite or finite assumption. So how do we know which one to use? Either one should give you approximately the same answer, but one might make more sense and be easier to assume than the other. Let's look into both assumptions, starting with the semi-infinite assumption. After noting the time dependence in the system, consider the length scale of the entire system, from one boundary to the other, source to sink. To use the semi-infinite assumption, the distance and time of diffusion must be small compared to the characteristic length of the system. Time is the only independent variable. The diffusion length scale is small compared to the depth of if the molecule of interest never sees or reaches the other boundary in the system within a short period of time. From these premises, we already have one constant boundary condition at x equals infinity. The concentration is the same as the concentration noted for the initial condition. We will consider x equals to 0 at the source boundary. Take a look at the table for the initial and boundary conditions. The table should help you decide when to assume semi-infinite medium. For a diffusion in a semi-infinite medium, the time scale is determined by when the concentration at the point of interest rises just above 0. When the dimensionless position, or eta, equals to 3, the concentration rises just above 0. We have also included dimensionless concentration, another important formula used in the semi-infinite assumption. You can also check whether the semi-infinite assumption is valid by checking that time t for the molecule to penetrate a distance L from the surface or interface boundary is t equals to L squared over 36 times DAB. For the second test, the length of interest must not have any molecule A reach it during the time period you're interested in. In other words, A does not see the boundary at L. Whereas the coordinate system in the semi-infinite assumption is rectangular from x equals 0 to L, the coordinate system in the finite assumption depends on symmetry. With the finite assumption, y equals to 0 is at the center line of symmetry. We can assume symmetry if the concentration of the source after a perturbation occurs is uniform on all sides of the system. This is the first boundary condition. Symmetry also means we only need to consider one side of the system. The symmetry assumption also gives us the second boundary condition at the center line. The change in concentration is 0, resulting in a 0 net flux. The flux is still one-dimensional if the system is much longer or taller than it is wide. That means that flux occurs in the wide direction. We have provided another table of initial and boundary conditions that are common for diffusion in finite mediums. The dimensionless variables are also compiled in the yellow table. A finite system will eventually reach equilibrium at a time tau equals to 2. A great distinction between semi-infinite and finite assumptions are whether the molecule of interest reaches a boundary or not. Also, semi-infinite and finite assumptions rely on very different coordinate systems and use different charts to approximate the values of the dimensionless variables. If you are finding the time to reach equilibrium or the concentration of the molecule after it sees a boundary, then you will most likely need to use the finite assumption. In summary, after determining you are at unsteady state, consider whether your molecule of interest reaches a boundary in a short period of time, or if the system can be represented with any sort of symmetry. Hope this helps, and I will see you in the next video.